And the first topic is going to be an application for derivatives. Now that we know how to find maximum and minimum using derivatives, the application for that is called optimization. So optimizing something would be like a maximize or minimize of something. So I know we have like maximize or minimize a variable. For example, how could a manufacturer minimizing packaging costs for a product? And so we're looking for like an optimal something, a maximum or a minimum. And if you remember, to find a maximum or minimum, there's two ways to do it. You take the derivative equal to 0 or derivative undefined. In most cases on these problems, we're going to focus on this. And then you put those values on a number line. Plus to minus will give you a max. Minus to plus will give you a min. Or if you want to, you can use the second derivative test for extrema, which is where you take the first derivative equal to 0, and then you just plug into the second derivative. And if the second derivative at that point is positive, you have concave up and it makes a minimum. And if the second derivative, is negative, it's concave down and makes a max. So bottom line, we're going to be doing like our find the maximum or minimum situation, which we have done in the past. But to begin with, we're going to be given a word problem. So we have a little like set of steps of how to work through the word problem. And again, that's something just special that we made up at our school, like at just Weddington High School. Students have this mnemonic device. We call it MEEPD, M-E-E-P-D. The M stands for determine if you're trying to find a max or min. The first E is for write an equation. The second E is for write a second equation. P stands for plug in, and D stands for derive. I will say that here in the middle, depending on the situation, your goal is just to have your function equal to something with one variable. So that when you take the derivative, you don't have to do anything implicit. We're used to our number line process and all that with just doing like an X in there. And it might be X or it might be like whatever letter you're using in the situation. But our goal in this process with the two equations is to sometimes use 3 equations or sometimes use 1 equation, like whatever it is that it takes to just have a formula with one letter. And I'll show you what I mean by that. Okay, so first problem. Find two positive numbers whose product is 192 and the sum of the first plus 3 times the second is a minimum. So I encourage you to first figure out what are we looking for? We're looking for a minimum. So note to self, I either need to do first derivative and get negative to positive, or I need to take my second derivative and it should be more than 0 because that would be a minimum point. So that's bottom line, the direction I'm going in. Okay, but then I've got to come up with the equations. So MEEPD. Okay, so M, this is the process I'm doing. So M means minimum. I'm looking for a minimum. Then your first equation is the equation that you're trying to find the minimum of. Okay, so this one, I look and say, like, let me read the problem again. What am I trying to find the minimum of? So it says find two positive numbers whose product is 192 and the sum of the first plus 3 times the second is a minimum. So I'm trying to the minimum of the sum. So I would do the sum is the first plus 3 times the second. I'm going to call that x plus 3y. So my first equation is whatever I'm trying to minimize. Then my second equation, I'm going to read the problem again and see if there's more information using both x and y that I can use as a second equation. So it says find two positive numbers whose product is 192. So my second equation is going to be x times y equals 192. That's my second equation. This is the one that I'm trying to minimize. This is a second equation that's going to help me with my next step, because my goal is to plug one equation into the other equation and just have one variable. So I'm going to go ahead and divide by, I guess you can choose here, divide by x on both sides here. So y equals 192 over x. And then my plug-in step is like substituting in place of y in that top equation. So x plus, okay, 3 times 192. So 627. Oops. I'm trying to write a 5 and I put a. So 576. Okay, so 576 over x. I'm just doing 3 times 192 over x. So that's my plug-in step. Okay, and my goal was to try to get just one variable, and I have now accomplished that goal. So I do my last step, which is take the derivative. So my derivative S prime is going to be X, we'll just go to 1. 576 over X, I'm going to think of that as 576 X to the negative 1. So it's going to become negative 576 X to the negative 2. Okay, and that's my derivative. So now I do derivative equal to 0 or derivative undefined. My undefined is going to be the denominator equal to 0, and that gives me 0. And then my equal to 0, if I put my equation equal to 0, I'm trying to erase some of this, hold on. That's... Okay, so if I put my equation equal to 0, I would just move this over to the other side. And then cross multiply the x squared over, or you can think of it as multiply both sides by x squared. And then I'm going to take the square root of 576 on both sides, and that will give me a plus or minus 24. And so I have 3 critical values. So on my number line, I would have negative 24, 0, and 24. But then when I go back to the directions, a lot of times I'm able to narrow down my answer just by what it says in the directions. And it says to choose 2 positive numbers. So this one is not going to work because that's a negative number. And this one is not going to work because that's not positive or negative. So I already know my answer is going to be 24. And when I go to do my sign test, I'm just going to check above and below 24 to make sure that I get the negative positive. So if I plug in, say, 23 to the derivative, or actually, let's just plug in 1. That's easier. So let me plug in 1. If I plug in 1, I would have 1 minus 576 over 1, which would give me a negative. Let me plug in a number bigger than 24, like say 100. If I do 1 minus 576 over 100 squared, that makes my denominator very large, and it's a number bigger than 576. So I'm doing 1 minus a number smaller than 1, which makes this positive. And so it's not a surprise that this is the minimum because that's the only thing that was left. But I know that my X value is 24. So my first number is 24. To get my second number, I have to go back to my equations where I did my substitution over here and look to see where I could plug in the 24 in order to be able to solve for y, which would be right here. I'm going to do y equals 192 over 24. See what that is. Which is 8, and so y equals 8. Now I could have plugged into this one also, whichever one makes more sense to you. But my 2 numbers are 24 and 8. Ran out of space here, but 24 and 8 would be my answer for this one. Okay, second problem. It says a rancher wants to enclose, wants to use some fencing to enclose 2 adjacent rectangular corrals. What dimensions should be used so that the enclosed area will be a maximum? Get some of these things out of here. Okay, so first I like to see, like, this is my process that I'm using. So am I trying to maximize or minimize? And I see the word maximize. So maximize is either on my number line, it's either going to go plus to minus, or I can take my second derivative. We'll practice with the second derivative this time maybe, and plug in. And to get a maximum, this would have to be less than 0 to be concave down and give you a maximum point. So I'm going to choose either one of those tests. But first, let me come up with the equation. So trying to maximize. Okay. What is it that I'm trying to maximize? The first equation should be the thing I'm trying to maximize. And I'm trying to maximize area, the enclosed area. There's 2 rectangles here, and the length of the entire figure is actually 2x, and the width is y. So the area is 2x, y. So that's going to be my first equation. The second equation is something that I go through and I read, and I try to find, like, what other information is there so that I can come up with a second equation. And that's gonna be the fact that there's 200 feet of fencing. And the 200 feet of fencing is like the perimeter essentially. So there's 2x on the bottom and 2x on the top. So that's a total of 4x. And then there's the left side and the right side, but there's also a fence in the middle. So I know we're thinking perimeter, but like your fence would also be going down that middle. So that'd be plus 3y. Okay, I think on this one, I'm gonna solve for x. And really you can choose either equation. I didn't say that in the last one. You can choose, either variable. I'm gonna solve for x because I would rather do 200 divided by 4 than 200 divided by 3. So move the 3y over first. Divide both sides by 4. They get 50 minus 3/4 y. My goal here is to be able to plug in and then just be down to one variable. So if I take this and I plug this in as the x value up there, I get a equals 50 minus 3/4 y times y. Oops, I forgot the 2, sorry. 2 times that, okay. So I get the 2 and then I replace the x and then I put the y. So I'm going to distribute the 2 and also distribute the y. So I get 100 y minus, when I distribute the 2, instead of 3/4, I'll have 3/2 y squared. And I've accomplished my goal of just one variable there. So now I'm going to do the derivative step. So my derivative comes out to be 100 minus, I bring the 2 in front, I just get 3y. Okay, then I take derivative equal to 0 or derivative undefined. There's nowhere that this is undefined, so that doesn't give me anything. When I put equal to 0, I'm going to move the 3y over and then divide by 3. So y is 100 thirds. So that tells me the y value, and the question says what dimensions should be used. Oh, sorry, let me do my second derivative test. I'm sorry, I skipped a step. Okay, so I can either do a number line with 100 thirds on it, or I'm going to practice this way this time. I'm going to take the second derivative. So a double prime, the derivative of this is -3. Pretty easy second derivative to do, and it's a really easy derivative test to look at, because since my second derivative came out to be negative, I don't even have to plug the 100 thirds in there. There's nothing left to plug in. Since I don't even have to plug it, like my second derivative is negative, therefore my graph is always concave down. Therefore that point is a maximum. Okay, so that verifies that yes, this is the correct point to use. It was the only one we had, so good thing it worked. And if it ever didn't work, then you would have to technically test endpoints. We're not going to go through that scenario, but it does work, so we're good. Then I have to plug back into one of the equations at the beginning to solve for what x is. So I can plug into either or any of these over here. I think I'll plug into this one. So x equals 50 minus 3/4 times y, and y is 100 thirds. When I do that, the 3's cancel. So I get 50 minus 100 divided by 4 is 25. And x comes out to be 25. When I go to do my dimensions, I definitely want to do like the entire dimension to make sure like I account for the fact that this is 2 rectangles together. So my dimensions would be 50, because it's 25 here and 25 here, and then by 100 thirds. And it's feet, right? Feet. So 50 feet by 100 thirds feet. I just realized I might not have put units up on that last question. Oh, because it's numbers, never mind. Okay, so this one, the units was feet. Okay, problem number 3, a manufacturer wants to design an open box having a square base with surface area of 108 square inches. What dimensions will produce a box with a maximum volume? So when it says the word open box, just so we understand this picture, there's not anything here. So it's like a, I don't know, like a crate or a bin or something you might carry stuff in. Okay, so when I look at my process, M, B, E, P, T. So I am going to maximize. And what is it that I'm trying to maximize? I'm trying to produce a box with the maximum volume. So I'm trying to maximize, my first equation here is gonna be for volume. And the volume of this is length